still hanging in there. All right. Well, I'm glad you're here. Excellent. All right. Today we are starting a brand new unit. This is a mini unit all about circular motion and a little bit of gravity. A few points of order though before we get started. First of all, some due dates have moved and shifted. First things first, we theoretically in the past had a U2 Quest that was due tomorrow. That is no longer the case. It is now due on Friday, and we're actually going to take some time in class this week to work on it. So it has been moved. It's still only like 10 or 11 questions, but I've bumped that out to Friday. The other ones, I don't think I've officially updated their due dates yet, but those will also shift back a little bit to match. So we will make sure that those all get done in due time, but worry about the first one first. The Atwood Machine Lab, I know was theoretically due on Friday. If you look at the link on my MCPS, the link on my MCPS has a due date of today. That said, I realize this has been a chaotic week/few days. So I'm going to just say I'm happy to accept the Atwood Lab through Wednesday without any 10% late fee or anything. After that, I would, it may be counted as late. Obviously, a couple of you have some extenuating circumstances in terms of time you've been out and different things like that. So come talk to me if you don't think you can get it done by Wednesday. I'm also going to make a small change. There is a MyMCPS link. If you've got it in a Google Doc, please turn it in online. That's going to be fine. Several people have done so already. If you happen to have it in your physical lab journal, normally, right, if you had turned it in your physical lab journal, where do I ask you to put it? Closet. I'm actually going to ask you, and there's a wonderful example here. Thanks, Kai. I'm going to actually ask you this time, if you've done it in your lab journal, so please put your lab journal here, because not everybody's going to be doing it in their lab journal, and I don't want to have to sift through and figure out who's done it in their lab journal and who's done it online. So if you've done it in the physical real world, you can put it here. If it's in the cloud, turn it in on my MCPS. Also, please continue to get me those exam corrections so I can get those updated. Hello, also to those of you who are joining us online. So this is obviously a little bit of a strange time. And I'm looking out at a number of smiling faces and, or masks that, and I'm not going to count on any given day for any particular person being here. So we're going to, over the next couple of weeks, try to make ourselves pretty robust to that. So for those of, we've got 2 people joining us online right now, which is great. For those of you who are online, I'm going to post all of those materials, all the handouts and notes and everything that we're doing, as well as this recording. I'll post it online by tonight. I apologize that it's not already ready. I will have that up by this evening. If you are at home, I'm also running office hours every day. Okay, every day except Friday. From 2 to 3:30 on Zoom. So if you are stuck at home, try to come to class. That would be great. Otherwise, you can always catch up with me during office hours on Monday, Tuesday, Wednesday, Thursday. I do want to say, if you're home and sick, be sick. Okay, rest, watch a dumb movie, binge all of, watch a bunch of Disney Plus or something. Yeah. So if you're sick, take care of your health first. Okay. Physics will still be here when you get back. That said, if you're just feeling better but waiting out the end of your quarantine or whatever, come to class. Come check in with me at office hours. Send me emails so that we can figure out what is going on. Yeah. On the homepage, by the way, you don't have to click on modules or anything. If you go to the MyMCPS homepage, you will immediately find 2 links. The first one is for Zoom meetings. So this is for they're both for Zoom meetings. The first one is for live class. So if you're attempting to attend 5th period, worth noting, right? If it doesn't work out for you to come to 5th period via Zoom, you could go to 3rd or 4th period if you don't have other classes to go to during those times, or they're not doing simulcasting or whatever. I also teach this period 3 and 4. So you can go to this link for live classes. If you're coming to office hours, there's a separate link for office hours just because office hours is shared with all of my other classes. So it's kind of a joint meeting. So that is there for you. Okay, let's talk about our warm up here. So I don't know where my things went. So Newton's first law, right, says that in the absence of an external force, right, an object at rest is going to stay at rest. But an object in motion is going to do something a little different. What's an object that's moving going to do? It's going to stay in motion, but it's specifically going to stay in motion how? With constant speed and constant direction, though, or what we call constant velocity. Because remember, velocity is a vector. It has a magnitude, which is also our speed, but it has a direction. So an object that has no external forces on it will move with constant velocity, constant speed, and a constant direction. What does my path look like? If I'm moving at a constant speed and a constant direction, what does my path look like? I'm a straight line. I will stay at rest or I'll move in a straight line. And this is super, super critical. Why is it super critical? Well, what happens if I see an object that's not moving in a straight line? What if I see an object that is moving like this? Or, you know, just hypothetically moving in a circle? What can I conclude? If an object with no forces on it moves in a straight line, what can I conclude if the object doesn't move in a straight line? It has some kind of force acting on it. If an object is not moving in a straight line, there's some kind of force that's causing it to deviate from its path. And so we can ask, hey, what force is that? So if I'm the Earth and I'm going around the sun, I definitely don't move in a straight line. So what is keeping the Earth in orbit around the sun? What's causing it not to move in a straight line and just kind of go off into space? Yeah, gravity. The sun's gravity is pulling the Earth into its orbit. And if I'm going to whirl something around on a string, I'll try to be careful not to hit anybody in the head with this. If I swing this around in a circle, it's not moving in a straight line. What force is causing it to not move in a straight line? Yeah, the tension of the string. And I know it's the tension of the string because what would happen if I were to cut this string? Yeah, this thing would go flying off in whatever direction it was moving. It would start to move in a straight line because once the force is gone, it would start to move in a straight line. So there's got to be some force, in this case, tension. There's got to be some force, in this case, tension. And one thing to note, right, is both of these forces kind of seem to point inward, right? They point towards the inside of our curve. And that's something that you're going to see a lot of. So welcome, by the way, to Unit 3. This is all about circular motion and gravitation. We're not going to get to the gravity part today. We're instead going to talk about the circular part today. What does it take for something to move in a circle? Because as it turns out, things moving in circles, or at least almost in circles, yeah, sometimes elliptical things or just parts of circles, comes up a lot in physics. Cars go around tracks, planets go around suns, and moons go around planets. Even things that only move in a part of a circle. If I let this thing go and it swings back and forth, because the length of the string isn't changing, the arc that this thing goes on is part of a circle, not a whole circle, but part of a circle. So circles come up a whole lot. So we do have a little handout. We got some definitions. Here we go. Ready? I'm going to blow your minds here. If an object is moving in a circle, the official physics term for that is that it is in circular motion. Whoa. I know. Galaxy brain moment. I'm just going to pause for questions on that. If it's moving in a circle, it's in circular motion. Just please note again, it doesn't have to move in a full circle. If you're sitting on the swings, and by the way, if you haven't gone to the playground and gone on the swings in a while, you should. Swings are one of the things that remains fun, regardless of whether you're like 3 or an adult. Swings are always fun. But if you haven't gone on the swings recently, when you're on the swings, the length of that chain doesn't really change. You are moving in a part of a circle. So even though you're not going all the way around, you are still in circular motion. Yeah, we're going to mostly ignore that. It mostly swings back and forth. Yes, you may. If an object, one particular type of circular motion that we're going to talk about a lot, though, is called uniform circular motion. When we say uniform, we do not mean that it looks, pretty. It hasn't been listed in the Navy or anything. Uniform circular motion just means that it's moving in a circle at constant speed, so that its speed is never changing. It's going, I don't know, 2 meters per second here, and later on it's down here and moving in a different direction, but it's still going 2 meters per second. So uniform circular motion. You'll see a lot of this word come up. They'll be like, oh, an object is in uniform circular motion. That just means that it's not speeding up or slowing down. It's just going around. Yeah. Yes. So, right. So you think about orbits. No orbit is ever a perfect circle. However, a lot of orbits are pretty darn close to circular. And it turns out that, and we're going to get more into this in the latter half of this mini unit. It turns out that ellipses are hard and circles are easy. And it also turns out, hopefully, that many of the things that we will derive for circles turn out to also apply to ellipses. So a lot of the things we're saying about circular motion are also generally true about elliptical motion as well, with some small differences. So we're going to start with circles because circles are easier, and then we'll extend to ellipses a little bit later. So uniform circular motion. All right. Sometimes we need new vocabulary to talk about things. So in this case, one of the things we want to talk about a little bit is directions. We do this a lot, right? When we started the year talking about, okay, what's the positive and negative direction? And then we started talking about like projectile motion, okay, the X direction and the Y direction. We even got a little fancy on ramps, right? Where we had like the parallel direction and the perpendicular direction. Right, so here's the problem with the circle. If I use the X direction and the Y direction, and I've got my little ball going around in a circle, which way is it moving? Well, okay, well down here, it's moving in the X direction. But if I wait a little while, now it's moving in the Y direction. And if I wait a little while longer, it's moving in the negative X direction. And over here, it's doing a little bit of negative X. Like the direction of motion keeps changing. So rather than trying to fix ourselves to an X and a Y, we're going to think about two new directions of motion. We're going to think a little bit about one direction, which is called the radial direction. And when we talk about the radial direction, you probably see in there a word that's pretty familiar to you when you're talking about circles, a radius. The radial direction is along the radius. The radial direction typically for us points towards the center of the circle. And note that this direction changes as the thing moves around. So when I'm over here, the radial direction is this way. When I'm over here, the radial direction is this way. But the radial direction always points towards the center. We have a radial direction that we care about. And perpendicular to that, conveniently, always nice to have two directions that are perpendicular, is what we call the tangential direction, which is a direction that's in the direction of motion, kind of tangent to along the circle. So this is the direction you're actually moving at any given moment. So my ball is going to the right. Now my ball is going up. Now my ball is going to the left. Now my ball is going to go down and to the left. So the tangential direction is the direction that it's moving at any given moment. So if you imagine that you're like a car on a track, like if you're a car driving around a circular track, it's a top view of a car. The radial direction is towards the center of the track. The tangential direction is whatever direction your car is pointed in right at that moment. So as you turn, right, your tangential direction is constantly changing, and so is your radial direction for that matter. But your tangential direction is straight ahead of you. The nice thing, by the way, about the tangential direction is like, well, we'll talk about more about that. So we got our radial direction and our tangential direction. All right. So let's talk a little bit about this kind of motion again. If I have a ball, oh, I meant to reset this. That's fine. If I have a ball, let's say it's going at constant speed. It's going around my circle, 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second. It's got constant speed. The question is, does it have constant velocity? And let's remind ourselves here that speed is not a vector. Speed is what we call a scalar quantity. It's just a number. But velocity is a vector. So velocity and vectors have magnitude. Quick side note that the magnitude of our velocity is just our speed. So our velocity has the same magnitude, 2 meters per second, 2 meters per second, 2 meters per second, the whole way around. Does our velocity have a constant direction? No, the direction is constantly changing. The magnitude of the ball's velocity is constant, but its direction is always changing. And so we actually have a word for this in physics, that if we change our velocity, we call that acceleration. So even though an object in uniform circular motion is not speeding up or slowing down, because it is constantly changing direction, the velocity is changing, and therefore we have an acceleration. So a ball with uniform circular motion, or any object in circular motion, is always accelerating. Even though it may not be speeding up or slowing down, it always has some acceleration. There's some acceleration required to change the velocity. So if I'm walking around the room, my velocity vector is constantly changing direction, even if I'm staying at the same speed. And anytime my velocity changes, that requires an acceleration. So in order to get something to move in a circle, it has to accelerate. Even if it's not speeding up or slowing down, there has to be some acceleration. There has to be some acceleration. All right. Specifically, we can talk a little bit about the direction of that acceleration. And it turns out that an object in circular motion is always accelerating, and that the direction of that acceleration is toward the center of the circle. No matter where I am in my orbit, if my ball is over here and moving this way, my acceleration, the required acceleration to keep me going in a circle, is always directly towards the center of the circle. We always have to accelerate towards the center of the circle. And that might make sense to you if you think a little bit about something on a string, right? If I kind of imagine swinging this thing around and I freeze it at some moment in time, right? Well, what is the force keeping this thing moving in a circle? The tension, right? Which way is the tension pulling on this thing? Pulling inwards. In order for something to move in a circle, you always need a force pulling it inwards. If you imagine standing at the center of this thing and swinging it around your head, you're pulling it inward the whole time. You're pulling it inward this whole time. And this inward acceleration has a special name. It is called centripetal acceleration. I'd like you to say that with me. Centripetal. Let's say it again. Centripetal. A little Harry Potter. Yeah. So centripetal acceleration. Centripetal, by the way, is a fancy word that means center seeking, which I like. It always seeks out, it always points towards the center. This, by the way, is going to seem like a somewhat familiar word to you, as contrasted with a word. There's probably a word most of you have in your head about circular motion in physics. Centrifugal. We will talk, not today, more about centrifugal force. Centrifugal forces and accelerations. This, by the way, means center fleeing. And it points in precisely the opposite direction. Please, for the moment, don't waste any brain cells thinking about centrifugal forces or centrifugal accelerations. We will get there. We will get there. All right. Well, it's about time we calculate. Let's do it. All right. So if I want something to move in a circle, we already know that it needs an acceleration. Turns out the amount of acceleration it needs is given precisely by this equation up here. that the centripetal acceleration is equal to v squared divided by r. This one, fortunately, is on your formula sheet for you. But let's unpack it a little bit because I don't want to just throw an equation at you. When I tell you that this is equal to v squared over r, what would you guess that v means? Yeah, it means velocity or speed in this case. So you take the speed of the object, you square it, and then we divide it by the radius. Yeah. Whenever you get it, if I give you a circle and I put an r in there, you're probably guessing that that r is the radius. So here we have the centripetal acceleration, v squared. Well, that's why we call it a centripetal acceleration, to note that this is the acceleration that's radial, not causing it to speed up or slow down. And it kind of can't, because it's always perpendicular to the velocity. It can't pull it forward or backwards, right? It's only pulling it straight into it. It's only changing the direction. So we also know, though, from our last unit, right, F equals ma. If I've got an acceleration, in order to have an acceleration, I need some force to provide it. So if I multiply my acceleration by m, I get this other equation, mv squared over r, which is what we call our centripetal force. And this is what we need. In order to move in a circle, we need something to provide centripetal. And these are the big equations that you need for this chunk of the unit. There's really only two of them, v squared over r. And if you multiply by m, mv squared. All right. Should we, this is a little circular motion here. Should we take it for a spin? Thank you. It's all right. You didn't think that was funny. You'll come around in time. All right, so let's take these equations for a spin. So here we have a student. She's whirling a 10-kilogram bucket of water around her head at a speed of 5 meters per second at the end of a 0.7 meter long rope. She looks remarkably calm about it too. So what I would like you to do is I'd like you to take 2 or 3 minutes and take these equations for a little stroll and see at your tables, can you calculate what's the centripetal? I suppose I wrote this in the wrong order. Doesn't matter. Go ahead and calculate the centripetal acceleration that the bucket will experience, as well as the centripetal force required in this case. So take a look. You've got it on your handout as well. So for those of you who are online, I apologize. The handout and everything will be online for you later today. So for the moment, you can follow along and just try out your calculations. Come around. Thank you for the reminder. I know a couple of you are back now, and yes, thank you. Let me take a moment. All right, let me see what we got for. Okay, we're waiting on a calculator. Yeah, those numbers are perfect. Come around, I want to see those numbers. Science mode. Couple seconds until the cat sound goes. Yeah, that looks good. let's make sure to put units on them. We got a force. Those are great. Let's make sure to put units on them. All right, so here we go. We've got our bucket coming around here. Again, why are we whirling an enormous bucket of water? I don't know. Like 2.5 gallons of water. Seems like a mess in the making, but in any case, ours is not to question why, ours is to calculate the centripetal acceleration. So in this case, v squared over r for the centripetal acceleration. Our speed is what? 5, so we can go 5 meters per second squared over, what's the radius of our circle? 0.7, right? It's the length of the rope. Now, you do have to be a little careful sometimes about the radius, UT Quest in particular. I mean, we all know and love UT Quest. We all know and love that UT Quest sometimes doesn't give us the information precisely as we'd like. So you always got to just double check. Hey, do I actually have the radius here, or do I have something else? So that's going to give us 25 over 0.7. In that case, which should give us 35.71. And it has units, and our units for acceleration are always what? Meters per second squared. And in this case, we can be extra sure, because if you look at the units, we square the velocity and we get meters squared over seconds squared, because we square it. We divide it by meters. One of the meters goes away, and so we get meters per second squared. So that's our acceleration. What the heck does that mean? One way sometimes that people like to contextualize accelerations is you've probably watched a movie or heard about G-forces, right? Or pulling 6 Gs, or training in 1,000 Gs or whatever for a certain anime. In any case, if I go ahead and divide this by 9.8, if I do 35.71 divided by 9.8, this tells me that the acceleration of the bucket is a little more than 3.5 Gs. So the amount of acceleration being applied to that, you were sitting in that bucket, it would feel like you were 3.5 times heavier than you are normally. It would feel like you'd be getting crushed against the bucket. Hey, biomed people, there's a fancy piece of equipment that swings a bucket of water around really, really, really fast. Centrifuge. And it does so by applying, the faster it goes, v squared, think about it, the faster it goes, the more acceleration you get, the more it kind of applies this force to separate things out. If we go ahead and look at our centripetal force, you could go back and calculate mv squared over r. You could also recognize that, hey, this is just F equals m times a. And so you could go ahead and multiply this by 10. 10 kilograms times our centripetal acceleration. So we get 357.1. And our unit for force is newtons. Newtons, yes. 357.1 newtons. Question. If I'm actually doing this experiment, I'm not going to do that because that's a lot of water and then I'd make it a mess. If I'm actually doing this experiment, right, what is providing that 357.1 newtons? Yeah, the rope. Now, ultimately, yes, it's the student's arm that's pulling on it. But if we're specific about the forces on the bucket, if I were drawing a free body diagram for the bucket, the thing that's applying that force is tension. And I know it's got to be tension. There's nothing else touching, right? And this is perhaps the most important part of this whole unit. You've got your equations. You are now armed with the ability to calculate your centripetal acceleration and your centripetal force. Here's perhaps the most important point. Centripetal force is lost behind my thing. Centripetal force is not a new kind of force. I want to repeat that. Centripetal force is not some new kind of force. Centripetal force has to be provided by other forces that we already know. So tension can provide centripetal force. Gravity can provide it. Even, as we'll find out, friction and normal forces. Literally any of the forces you know about, magnetism, electricity, can provide these centripetal forces, but centripetal forces are not themselves some new force. So you should never, ever, ever, ever have a free body diagram. Exactly. You should never, ever, ever have a free body diagram where you're like, oh, well, here's gravity down and normal force up, and here's centripetal force to the side. No. Centripetal force is not a type of force. It's just a description for it. Hey, this is the force that's causing something to move in a circle. So what we say is that if you've got something moving in a circle, the net force in the radial direction needs to be equal to, oh, what was my equation for the centripetal force? mv squared over r. mv squared over r. So we're going to do some more problem solving in a moment. My watch is actually not set properly, so I've got about 5 minutes left. I got about 5 minutes left. We're going to start a practice problem in just a moment to get a little bit deeper into this. But I want to pause for a moment and just reiterate how critically important it is to remember this equation. Because you're going to see over the course of the rest of the year lots and lots and lots and lots and lots and lots and lots of problems where things are moving in circles. The moment you see a circle on your sheet, you see the words a circular track, something's moving in a circle on a string, you should hear in the depths of your brain, as though carried on a distant breeze by a faraway voice. It does not matter what the context is. There is a circle, there's an mv squared over r in there somewhere. So that is really, really important to keep in mind. All right, let's take a look at an example. We are not going to finish the example today, but we're going to start it today and we'll finish it tomorrow. And we'll work on our UT quest as well tomorrow. So how do we actually do a circular motion problem? Yes, sir. How do we actually do a circular motion problem? Well, because there's forces involved, one of the first things we always want to do if we suspect there's forces is to do what? Draw a free body diagram. Yes. So the first thing is it moving in a circle or even part of a circle? Do you suspect? Does it smell like a circle? You touch the ground, like on a police show, you touch the ground. A circle is here. Yeah, no. Sherlock Holmes stuff. No, if you suspect that there's a circle, then there's got to be some centripetal force, that's circular motion. So the first thing you're going to do is you're going to draw a free body diagram for the system. And then you're going to look at your forces. And what you are going to demand is that in your radial direction, the direction that points toward the center, your net force needs to be mv squared over r. If your net force is not mv squared over r, you're not moving in a circle. And then you can also look at, I misspelled tangential. You can also look at Newton's second law in the tangential direction. Usually the forces in the tangential direction will add up to 0 in this class, because mostly we're dealing with uniform circular motion. It's not speeding up or slowing down. So let's take a look at a little problem. And we're going to do the first bits of this today. We're going to try to draw a free body diagram and get going. So I would like to take you back to a merry-go-round. So here we have a child, a 12-kilogram child. So this is a toddler, actually. A 12-kilogram toddler stands 2 meters from the center of a merry-go-round. The merry-go-round rotates 8 times per minute. We're going to get to the final question later, which is about friction. But what I would like you to start with is, see if you can sketch. We're going to take the remainder here, and I'm going to come around and help you see what you're doing. I would like you to sketch a free body diagram for this kid. You should have, spoiler alert, there should be 3 forces on it. And then as a little speculative thing, we're going to outline a procedure for it tomorrow, but I want to see what you can do. Can you figure out the child's velocity? I do give you enough information to figure out the child's velocity, but can you figure out in meters per second how fast the kid is actually going? So that's your job for today, is to sketch a free body diagram for the kid and see if you can figure out the velocity. I keep looking at my wrist, but I haven't actually set my watch properly today. So, oh, well, we only have 1 minute. Should we just sketch the free body diagram together? Yeah? Okay. You tell me, what goes on this free body diagram? All right, well, let's start with the ones we definitely know. Which is? What's a force on this kid that we definitely know? Gravity. we've got gravity down. We have normal force up. All right. Now here's the thing. He's moving in a circle. There's got to be some force that points towards the center. Well, if the kid's not holding on to anything, there's nothing that isn't in the drawing. There's not a handle that they're holding on to. There's no string or anything. What is the force that's available? Friction. And specifically in this case, if the kid is going around in a circle and isn't slipping or falling off, what kind of friction? Yeah, it's going to be static friction. It's going to be static friction. So what we're going to do tomorrow when we come in is we're going to use this and we're going to break down, hey, that static friction force is going to need to provide mv squared over r worth of force. Because if it doesn't, if static friction can't provide this force, what's going to happen to the kid? You're not going to move in a circle anymore. And it turns out if you're on a merry-go-round and not moving in a circle, you're falling off the merry-go-round. Or you're just floating above it. Yes, or you're mysteriously hovering above it. But the kid has no psychic powers so far as he's going. Imagine it. That would be part of the problem. They would tell you. That would be a whole new class. Assume psychic powers are negligible. Ignore PSI. Yeah, I did publish it. I clicked publish on it. I will try to download it. So sometimes they sign out. So now we have. I'll post that up.
Yeah, something like that. Yeah, like say this us was like different. So pretty much like in universe, it was us.
So I will Eric is asking yes. It could also would probably be more effective. I have to run downstairs real quick to make an announcement. But then if you want to hang around, I can do it. Or if you wanted to go and come back.
Okay, yeah, I have some things to do, but I will be back.
Okay, and if not today, we can get on. Yes.
Just a friendly reminder that credit recovery for U.S. history, NFL, modern world history, 45 after school. U.S. history meets in Rome 2001, NFL meets in Rome 2017, and a modern world history meets in Rome 2012. Again, today, making sure that students are reminded that we have credit recovery for U.S. history, NFL, and modern world history.
They haven't done the P-lab. Okay.
Attention, Weekend Science Bowl members, members of Weekend Science Bowl team. This is Mr. Bates. Please report to room 3204 for a rescheduling meeting. Science Bowl to room 3204. Thank you very much.
Every pound of random material you find in this they wanted the kind of materials you wouldn't really go sell. So, you know, sell.
Oh, I think, okay, I'm probably gonna.
Sell them on.
I'm not.
Yeah.
So I think what I'm gonna do is I'm just gonna put this,
I'm still getting that good stuff. I don't even know what spell it is. I don't even know. I don't have a responder. I didn't make one. I think I still have a rocky top.
yeah, I think everything's still.
Oh, wait. I didn't know that. Wait till the right time and say, hey guys, I'm 75 miles away.
Oh, yeah. You can't.
No. I actually, oh wait, what's the range? Okay, never mind. I can on it. Well, not long. Not long. When it asks when we reach the destination.
Yeah. I really like one or two diamonds. It was just like me.
Sorry. Yeah.
Send me. Yeah, I'm a one.
Yeah, you're one. But everyone.
Yeah.
You're gonna be at four.
Yeah, I guess it's double.
Right, you weren't there. You were dying.
Oh yeah, you weren't there. I'm sorry. We just died. That's the greatest.
Yeah.
Okay.
Oh, yeah.
Imagine.
Grab the seat. Ooh. You are permitted to use school of elevation.
Yeah, that's right.
I got the bullets for you.
Everyone else got it.
Well, that's what also be.
Exactly.
I wasn't there, so I didn't. All right. Well, maybe you could play green. I know Hudson wants to come.
Everyone. I just want you to call it an actual work.
No? Okay.
No, which one was like a good one?
Well, now we do. I have a good one. I have, in this case, two that are missing. I have one. And one is, what is still?
What is it?
Hey, can I get one?
I just myself off some stuff I know. Like,
What?
you know, but like you have a white.
Oh, yeah, yeah. Yeah.
Woohoo, this is very weird. It's very weird. Original. They just vanished.
Just.
Yeah. All of them started walking. All of them
We
just
are.
they all left.
In my channel called Cool DM Chat, where I live by myself. Okay.
All right. So, science goal peeps, how you doing? So,
No, we do science for less.
things to be aware of. Oh, I should probably stop this Zoom.